How's it going, everybody? This video I'll be talking about cubic functions. So our objectives are pretty simple. I'll be looking at 3 different ways you can explore a cubic function. So the first way is just with numbers. And the second 2 ways are algebra that's going to build off of the algebra that you already know for quadratics. In fact, everything you're going to see here about cubic functions is something you've already sort of seen with quadratics, just generalized to the next step. So that's what we'll be talking about. Let's start with a little motivation, okay? So as a quick recap, right, let's just start with the numbers, right? We've learned how quadratic number patterns build off of linear number patterns, and linear number patterns build off of constants, right? So what we mean specifically here is when you take the rate of change, or in other words, with just a number pattern, all the rate of change means is how much it goes up or down by each time. If you start with something that's quadratic, what that means is when you look at how much it increases or decreases by each time, you get a pattern that's linear, right? And you can recognize a linear number pattern if when you take the amount of increase or decrease each time, you get something constant. But this begs kind of an obvious question, right? So if linears build on constants and quadratics build on linears, what builds on quadratics? And of course, I guess, spoiler alert, by calling the name of this video cubic functions, cubics. If a quadratic pattern changes like the area of a rectangle, then a cubic pattern should change like the volume of a cube. So let's look at this. Let's fill in the gaps here and see what this means if we just look at the numbers. So here I have shown 3 cubes, right? And if I ask about their volumes, well, it's pretty easy to compute the volume of a cube, right? Volume just means how much space the cube takes up. So you can imagine this is like, a 1 foot by 1 foot by 1 foot box, and you're asking what the space is. Well, that's just 1 times 1 times 1, or 1 cubed, right? And similarly with these other boxes of different sizes, right? And if we look at the pattern here, okay, so for the first one, we'll get 1 cubed, which is equal to 1. Incidentally, that's why raising to the power of 3 for a number is called cubing it. Just look at the picture, right? 2 cubed is 8, 3 cubed is 27. And these numbers correspond to the volumes of the boxes shown below, right? 3 times 3 times 3 is 27. 2 times 2 times 2 is 8. Okay, so if we have this pattern then, and here I've written it all out, here's the volume of the cubes, right? So first is 1 cubed, then is 2 cubed, then 3 cubed, 4 cubed, 5 cubed. If you're really good at mental math, you can get the rest of them, right? But anyway, I've just listed out the first several volumes, okay? And what happens if we take the rate of change? Well, let's look at this, and we kind of already know what the answer is going to be by the discussion from a minute ago, okay? But if I look at how much it goes up by each time, I put these numbers in blue. From 1 to 8 is an increase of 7. From 8 to 27, an increase of 19. 27 to 64, an increase of 37, and so on to get these other blue numbers here. Okay, well, you look at the blue numbers, you say, well, I don't quite see the pattern yet, but let me do it again. Let me take the rate of change again. So maybe these blue numbers have some nice structure to them, right? So from 7 to 19, how much does it increase by? From 19 to 37, how much does it increase by? And so on. And if I do that, I get these little pink numbers here. And the pink numbers seem pretty clear that there is a nice pattern. So while we looked at the original black numbers, it wasn't so clear. I mean, we know that they're the volume of cubes. I showed you that that's where these numbers come from. That's what's motivating them. But if you didn't know that already, and you were searching for patterns, what you might not have realized is that there is some really nice structure here, right? So taking the rate of change twice gets me this pink pattern, and notice the pink pattern increases by 6s every time, which means what? That means if the pink pattern increases by 6 every time, the pink pattern is linear. And if the blue pattern increases by this much, which is a linear, that means the blue pattern has to be quadratic. Whoops, and in fact, that is exactly what's happening here. The cubes, the volume of the cubes, whoops, the volume of the cubes increases. How much does it increase by? Well, that's this blue pattern, which is quadratic. Why is it quadratic? Because it increases by a linear in pink. Why is that thing linear? Because it increases by a constant amount. And so that's what I get here. You can tell if a number pattern is cubic by finding its rate of change. Its rate of change will be quadratic, right? And so you get this nice hierarchy. Cubes build off quadratics, which build off linears, which build off constants. Okay. The algebra reflects the numbers. Okay. Since cubic number patterns build off quadratic number patterns, then cubic functions will build on quadratic functions. And we'll see this in two ways, starting with the standard form. So here's the standard form for a cubic function. The boxes indicate that you should put some numbers in there, right? So you'll put different numbers into these boxes and it'll build you a different cubic function, different cubic models, okay? So here's what it looks like. And you notice now if we look at this thing closely, if I just look at these first two terms, the yellow box and the blue box, right? And if I were to say, what is this, what is that, just that part of the pattern, you tell me it's a linear pattern, right? This is like y equals mx plus b if it was just this piece here, okay? But what's going on? Again, quadratics build off linears, cubics build off quadratics, and I see this in the algebra, right? If I now add the third term, the green box term, the squared term, then those three pieces together make a quadratic. Notice the linears contained inside the quadratic. And then all together, I get a cubic. So the cubic adds the cubed term, the x cubed, onto the quadratic. The quadratic adds the squared term. Remember, quad means 4, like the area of a square or a rectangle, x squared here. We add that onto the linear piece, okay? So in standard form, we decompose the pattern into each of its constituent pieces, right? In this case, we're looking at the cubes, the squares, the lines, and the constants, and that's what those colored boxes are. The blue box is the constant box, the yellow box is like how many lines, or you could think of that's like the rate of change of the linear part. The green box is like how many squares or like the rate of change of the quadratic part. And the pink box is like how many cubes or the rate of change of the cubic part. Okay, right? So again, we're doing the same exact thing. Like just like you understand y equals mx plus b, and that yellow box there is just the rate of change of the line, that builds into a quadratic, which has its own rate of change, and we can build onto that to get a cubic, right? So this pink number will tell me how fast the cubic part of the pattern changes, or how many cubes are in the pattern. Okay? But just like with quadratics, we can, standard form isn't always the way, it's not always the most natural way to represent a pattern. We saw this with quadratics, right? So just like with quadratics, we can do the factored form as well. Well, okay, a volume of a cube has 3 factors, its length, width, and its height. And of course, we'll see that the algebra of a cubic function will also have 3 factors. Now, there are some technical things here that I don't want to get into right now, but generally speaking, this is true. Okay? And so if we look at the factors are like the dimensions, right? Like a box has 3 dimensions, right? If I look now, just like before, my cubic should build off my quadratic should build off my linears. So if I have a function that's v equals x plus 2, well, you would tell me that's a linear function. This is like mx plus b. But now if I add in another factor to that, you would tell me it's a quadratic. If it was v equals x plus 1 times x plus 2, now I have 2 factors. This first factor you could think of like the length of a rectangle, and the second factor as like its width, perhaps. Okay, but we see that we've added another factor to get me to a quadratic, right? And then, of course, cubics, well, you can add another factor to that. This is just an example, and I have a picture of this in a minute here. But notice that now the cubic will have like the length, the width, and the height. And when you multiply those 3 numbers together, you get a volume. When you multiply the 2 factors together, you get like an area. That's like this quadratic, the area of a square. And when it's just one direction, it's like a cool pop band. No. If it's one direction, it's changing like a line. If there's two directions, length and width, it's like an area of a rectangle. If there's three directions, maybe you could make a cool new band called Three Directions, and you'd be all about cubics. Anyway, so here I just have a little illustration of that idea. Like you could imagine that, I'm using variables here to represent the dimensions of this cube, and it's x units across, and it's x plus 1 units deep, and x plus 2 units tall. So you multiply those three numbers together to give you the volume. And what's interesting to notice here is like each one of these individual factors, right? If I just look at the x, right, that's like really, it is literally just like a linear piece, right? It's telling me how long it is, right? When I multiply the x and the x plus 1, that's like telling me the square footage of the floor in the cube, right? And that's why it's a quadratic. It changes like, I guess it's a rectangle, not really a cube, but it changes like area. And when I multiply all three, it gives me the space, right? And so I can see the linear living inside the quadratic, living inside the cubic in this factored form. And if you wanted to like get this into standard form for some reason, you could multiply these things all out, and it would look like it's in standard form. But in this example, right, it's much easier to see the three different factors because we're computing a volume here. Okay. So in summary, you can check if a number pattern is cubic by seeing if its rate of change is quadratic. The standard form, the so-called standard form for the algebra, for a cubic builds off the quadratic by adding this little cubic term. And in factored form, we add an extra factor, so we'll have three factors for a cubic function. So anyway, thanks for listening and have a good one.